Hey everyone, it's YK from TDS and CS Dojo here. And today I have an interview I did with Chanchal, who is an AI leader at Google. In this interview, we talked about different projects he worked on, including some financial applications of AI, one research-oriented project, and making conversational agents. I personally learned a lot from this interview, so hopefully you will too.
Yeah, so my name is Chanchal Chatterjee. I'm in Google Cloud. I work for Google Cloud Professional Services Organization. I'm a ML AI program manager. I lead customer projects, and I also help customers discover their ML problems.
Okay, and I saw that you're an AI leader or leader in AI, something like that.
Yeah.
What does that mean exactly?
Well, the AI leadership, first of all, Google is a leader in AI, and what we do is to lead projects for customers. And so that's sort of the leadership role. But in Google, we all work in a collaborative fashion. So there are extremely extraordinary engineers, ML engineers that work with me. We also have partner engineers. So customers come to us to solve ML problems. Some of them are trying to take their models to the AI infrastructure that Google provides, and some of them is to build new models for them. In all these projects, we deliver an end-to-end solution to the customer.
Right.
Those are the projects I lead.
I see. So I'm guessing that you interact with both customers and engineers.
Yeah. So in order to manage those projects, you have to work with customers, and some of these projects also have engineers from customers. So the team may not be all Google engineers. It can also have partner engineers, and it can also have customer engineers in those teams.
Nice.
So it's a very deep interactive experience for the customer in order to do the development of ML solutions. Like I said, I'm a practitioner of ML, not a researcher.
I see.
Although some of these projects end up being published as research papers, like a project we did is being published in NeurIPS. NeurIPS.
Right. Yeah. Could you tell us about that project?
Yeah, so my specialization more in the financial services. That was sort of a one-off project we did for an energy company in order to do subsurface exploration, and we came up with some pretty cool algorithms with generative adversarial network and known as Gantz, conditional Gantz, and we produced some very nice research, and it's getting published in the NeurIPS workshop in Vancouver.
I see. You said subsurface?
Subsurface, there's a type of data that you gather from subsurface called seismic data. It comes in multiple varieties. One is 2D, two-dimensional, three-dimensional. So we took these two-dimensional, three-dimensional data. We put some constraints on what is called constraints on the different type of rock surfaces, which is known as lithology. And based on that, we came up with clear enhancement of the subsurface picture. So that's what we did.
I see.
In that project. But we do many other projects for financial services, for retail, for media and entertainment, for manufacturing, all kinds of verticals. So I'm focusing primarily on financial services.
Okay. Maybe you can tell us about what you usually work on then with financial services.
So financial services, there are plenty of use cases. Fraud, I would put them in two categories. First one is where you do revenue loss prevention, which things like fraud and anti-money laundering falls in that category. The second one is in the category of revenue generation. So those are projects in which you want to do interest rate prediction, margin prediction, profit prediction. So if a customer is selling equities or different types of securities, whether mortgage or equities, and the customer is the owner of the equity, they're called dealers. They sell it to the buyers. And then the dealers would want to know how much margin or interest to charge. So that's the revenue maximization problem. There are also situations where brokers would borrow equities in order to short them in the future. So if some lockup period is ending in a certain stock and a lot of employees are going to sell it, so that's a favorite time for shorting a stock. So a lot of brokers like Goldman Sachs will buy those equities from large equity holders like Fidelity and Charles Schwab and all these companies, and then they will sell it in the market, and then they will buy it when the price is lower and give it back. So there, the equity owners would like to know how much to charge. So that's and the third category of projects we are doing for financial services are like AI infrastructure. They already have a lot of quants and data scientists that have built models, and we would bring those models to the Google's AI infrastructure. Make sense?
So the models are built by quants and
Yes.
engineers?
So customers know better about their problem. So they would build like models for, let's say, loan delinquency prediction is a model they have built, and they build a certain type of model that they are used to. Like they might build with algorithms, not necessarily deep learning or very deep machine learning algorithms. They might build with simpler algorithms like a decision tree. But building a model is one thing, on a static set of data is one thing, but making it production ready is a completely different thing, which means that as your data is changing, you have to rebuild the model, you have to store and tag the models, or what is called metadata, and then you have to serve the appropriate model when you have to predict. So that whole end-to-end, so you have to pre-process the data, you have to train the data, then you have to train the model, then you have to save the model, then you have to serve the model, then you have to explain the model. These are all distinct steps that you have to do on a continuous basis. And that whole thing is provided by Google's AI infrastructure.
Google's AI infrastructure.
Exactly. End to end. I presented a little bit of that today.
Nice. Is that part of Google Cloud?
This is all part of Google Cloud, yes.
Is it publicly available?
Absolutely publicly available. Any customer can go in and take, you as an individual, you can get some free credits and start working on it. As a startup company, there are even bigger amounts of credits that are offered by Google in order to get started on the Google Cloud. We also offer training. There are also publicly available training like Coursera. You can also get Google sponsored training, partner sponsored training. And if none of that worked for you, you can hire people like myself from the professional services in order to build that all out for you.
I see.
So many ways to do it. There are three basic ways by which you can do machine learning on the Google Cloud. One is you can start from scratch and build your models. This is what we call your data, your models. You bring in your data, you build your models. So you have some trained, experienced data scientists, those who know machine learning can handle this, or you can hire our partners, or you can hire professional services to do it for you. The second model of doing machine learning that we have is what is called AutoML. In AutoML, we have already defined certain models, not trained them, but defined them. But this comes on a fixed set of categories like recommendation, tables, for structured data, speech, natural language processing, API, vision, and so on and so forth, video intelligence. So there you bring in your data and you can train it with these predefined models, and then you can deploy them and scale them. The third one is API. These are pre-trained models. These are trained with our data, and you can just simply bring in your data in order to run prediction on them. Okay? So that's the third way of doing machine learning. And the do-it-yourself model, where you bring in your data and your model onto the cloud, there are two basic ways of doing it. One is called the Cloud AI Platform, which is where you take your model, you break it apart, and you implement in the cloud, in the Google Cloud, so that it's scalable, okay, exportable, and you can basically scale it horizontally, vertically with workload, and it's maintainable. It's fully maintainable. All the models are stored in the repository and so on. The second way to do it with Kubeflow and Kubeflow pipelines. That's a newer construct and a more wonderful construct in the sense that you can also have the additional features of composability and portability. That is, you can take your machine learning problem, divide into composable units, and you can port some of that into on-prem environments too. And it becomes a Dockerized container based.
I see. What's a typical machine learning or deep learning architecture look like?
So a typical machine learning architecture will have the basic components, which is data preparation, feature engineering, model selection, model training, model repository, model serving, and model explanation. These are the basic pieces. And the other thing about AutoML is that all these pieces are under the hood. You don't have to worry about them. You just ingest the data and you just do the prediction. But when you build it yourself, you have to build all these pieces. And there are lots of papers here, people talking about the entire data preparation pipeline, which can be very complex. If you don't have labeled data, how do you label the data? That's also another layer of complexity. So data preparation itself is a big part of the job in machine learning. It starts with data, and therefore all those are individual components of a machine learning pipeline.
Okay. So I think I'm gonna switch the gears a little bit and I want to talk a little bit about your background.
Okay.
So I understand that you have a PhD in electrical and computer engineering.
Yes, I got a PhD in machine learning, actually in adaptive learning, back in 1996. And the way I got into machine learning is because prior to that, I was also working at a company. And while I was doing my PhD, and we were doing optical character recognition back in the mid-90s, before all the sophisticated character recognition solutions came in the market, and we were working with inkjet characters, where the characters were changing constantly. So I wanted to design a solution by which we will put a machine which will look at the characters one by one as they come through, and after 1 hour, will have a perfect training template for that character, for all those characters, like if it's A through Z or 0 through 9, whatever. And then, and this training will create the proper models for each of the characters so that you can simply learn them. But what I did is I didn't know how to go about doing it. So I went to Purdue University and met my professor and said, I want to figure this out. And then we got into this area of adaptive learning, of how to take samples one by one and learn them. And that's where I got into this whole area of modeling and model training and all of that. And then it became more and more complex from there. So that was the beginning.
Right. So it seems like modeling and model training is really the part of machine learning that excites you.
That was very exciting, yes, because it automates a lot of the manual process, and it also helps you discover things that you would never find. Like the other area that excites me tremendously is model explainability. Like if you train a model on a huge number of features, let's say you want to predict a stock for next 2 days, then you have a huge number of features like the company, the value, market value of the company, the Morningstar rating, the current value, and so on and so forth. And then you take all these features and then you went and predict the next value of the stock. And then the most interesting thing is, what is the best predictor? Is it the market cap? Is it the Morningstar rating? Is it the previous valuation? And to find that insight through a model explanation is very cool. Is to understand and how the model works. Like today, somebody was giving a talk and they showed that the model has recognized a husky dog. And then when they did the explanation, they found that all they were using in the model was the picture of the snow behind the husky. You see what I mean? So clearly the model didn't do a good job. If you put the husky in a green background, it will not work very well. So the model explanation is a very valuable topic, and I'm very excited. So I'm working both on the AI infrastructure as well as on the model explanation, are two very exciting topics for me.
I see. How do you find explainability in a model?
So explainability is a very complex topic, but explainability has many audiences. One audience for explainability in financial services is the regulators, because they want to know how you built the model, if there's bias in the model or not, and so on and so forth. The second customer for model explainability is the builders themselves, okay? The software engineers that are working on the model. So they want to create increased understanding of the model. So regulators want to create increased trust. Developers want to create better understanding. The third one is consumers, who also want to understand, like somebody walks in and gets a loan and gets rejected, they want to know why they got rejected. So that is also a trust and transparency issue. And so these are the three main categories of audiences. So there's a lot of science behind it, there are a lot of techniques. Google has a special technique called integrated gradients, and we use that in order to find basically explanations about the model. There are two types of explanation. One is called global, which is taking the whole aggregate of data and understanding it. The other is for an individual event, what was the reason. So there's lots of depth in it.
You say integrated gradient?
Gradients, yes. So the integrated gradients is basically based on the idea that the model itself has internal features or internal items called gradients that change as the input changes. So what they do is they take over a variation of inputs, they integrate those variants together and create an explanation out of it. That's why it's called integrated gradients.
Okay.
It's a very exciting technique. So, but the main crux of model explanation is to understand why the model behaved in a certain way. It is to create trust, it is to create transparency, it is to create compliance, and it is to create better models.
Yeah, that sounds like a pretty hard problem to solve, though.
It is a very hard, and it's a work in progress for the entire ML community. I think the AI infrastructure is also very, because it's such a rapidly moving field, that new algorithms, people are inventing new ideas, but there are more ideas coming than being used out there in the field. So a lot of the people are wondering, okay, so we got a beautiful model working very well. How do I take it to production? How do I make it easy? How do I break it up into components, which is composability? How do I port it between the cloud and my on-prem? How do I make it export to other environments? And how do I scale? And how do I maintain it? Maintain and manage it. So if you are a manager and you have 20 data scientists working on models, your first question will be, okay, so I have a model proliferation problem. So how am I going to manage all these models, right? And data also changes constantly, so you have to keep building these models. So bringing model to production is a non-trivial process. And the cloud infrastructure provides that for you.
Right. The Google Cloud infrastructure.
Yeah, Google Cloud among others, yeah.
Oh, among others, right. Yeah. Yeah, so that's more of a software engineering problem then.
It's not entirely, I would call it ML ops, more like ML operations, rather than ML dev. So when you talk about software engineering, it's more like development, but it's software engineering in both cases, but ML operations is more specialized in how to bring ML models into production.
Okay. I'm kind of curious, do you ever work with any Google products internally?
Of course.
Okay.
We work with Google Research. We take brand new research and bring it to the market. We had this particular research that is getting published in NeurIPS. We did not have a construct for building conditional Gantz, that worked with the TPU. We needed to use, Google has a specialized hardware unit called Tensor Processing Unit, so we went to Google Research, brought in the most recent software and made it work.
Okay. So you needed to build a new set of software just so that it works with TPUs?
That instance, but generally
Okay.
we have what is called estimators, which basically are constructs where a model can be used either on a CPU, GPU, or TPU. In this particular instance, we didn't have it. That got built. It was an alpha release that we used.
Right.
But since then, that has been released.
Okay. So I've heard of TPUs, but I'm not too familiar with them.
So TPUs, they're special hardware processing units that Google has built. It is basically specialized to use TensorFlow on the Google Cloud and make it efficient. And a lot of open source research have done a head-to-head competition against CPUs and GPUs. One of the famous organization is called DAWN, DAWN by Stanford, and they have shown that TPUs have done very well. I can only speak from my own personal experience. I was doing a very complex project in which I had a huge quantity of data coming in, and they did not fit into the GPU's memory. So we moved to the TPU, and we could only fit only one data point into the memory to do the training. It's called batch size, which is very bad. So we could move up to 16. And then also we could do 3x more training. So we had 3x more speed and 3x less cost in that project.
Compared to GPUs.
Compared to GPUs. But GPUs are a very valuable thing for us, and we use a lot. So I'm not going to say GPUs are worse or anything. GPUs are very good, and NVIDIA is constantly innovating. But in this particular project, the TPU was extremely helpful.
I see. Depends on the project then.
Yeah, it depends on the problem, certainly. In very complex problems, which requires a lot of compute, a lot of data, I have seen that in some of my projects, TPUs have been very helpful.
I see. Is the rule of thumb then, if there's a lot of data, try TPUs?
Not necessarily. It's very project by project. It's a ML design issue. But I would say that if you could use the GPUs, you should use it first. And if you cannot use the GPUs, then explore the TPUs for sure.
I see.
That's the path we took.
Okay. Is there any research that you've done that was actually brought to like a particular Google product?
So no, not really. I haven't done any research. Like I said, I'm a practitioner of machine learning rather than a researcher of machine learning. We haven't done any fundamental research, but we have implemented some very exciting models for the customer. We are trying to make machine learning simple, machine learning easy to use, and bring customers' machine learning workloads to the cloud. That's basically my role. Not to invent new research, although our paper on the seismic exploration, which we did jointly, has been tagged by Google Research as one of the papers. So that's the only contribution I have on the research side.
Okay. I'm kind of curious about it, and I think we have a bit more time, so maybe we can talk a little bit more about that research.
Yeah, so that research, as I said, was on conditional generative adversarial network. So basically the idea is that on the Earth's subsurface, you have different types of rock structure. So when you take these images, they send these waves underground, and they take the reflection of the wave, and then they do some physics-based mathematical processing to create a three-dimensional volume out of that. That is called seismic volume. So those volumes are not very high resolution. High resolution pictures are very expensive. So one of the things that the oil companies want to do is to take these low resolution pictures and enhance them. But when you enhance them, then you have to be mindful of the different types of rock structures underneath. So if you conditionally enhance the image based on the rock structure, you get a better enhancement than the without conditioning.
Right.
And in order to do that, you have to basically take a large volume of image data, divide it up into smaller volumes, and you have to run some complex algorithms through a very deep neural network called generative adversarial networks in order to generate the enhanced volumes out of it. So we did a lot of research on trying to find out how the conditioning input should be inputted, and how the conditioning input should be used into the processing, whether it should be additive, multiplicative, whether it should be there in the beginning, in the middle, or at the end. All these different aspects we did the research on, and we found an optimal solution. We also used one of the tools in Google Cloud called hyperparameter tuning in order to find the optimal way to combine the conditional information with the original seismic image in order to get the best generated image.
Because I'm not too familiar with this particular field, I'm going to ask this question. How do GANs work?
So GANs have two layers. One is called generation. So it takes what is called pure noise or low resolution and it generates the high resolution. Okay. The second is the discriminant. It basically takes the original high resolution, it compares with your high resolution and gives you a score. So the idea is to optimize the discriminator and the generator so that you maximize the score and you create the best possible discriminator and generator. So basically it's a min-max problem. In one, you are generating an image, you can now compare against the original and trying to minimize the gap with the original. So it is also used in many other use cases like fraud detection. I've seen check fraud detection papers with GANs. Like you take a check and you generate a check out of that image and you compare it against a real check and see if it's a fraudulent or not. So basically we take the low resolution, generate the high resolution, and that's the generation process. Then we compare with the real high resolution through the discriminator process in order to create the score, and we minimize the score so that we get the best generation.
I see.
That's how GANs work.
So with your particular research, you had these inputs and you were trying to recreate a picture?
So we're taking the low resolution, we're passing it through the generator to get the high resolution, generated high resolution. Then we take the generated high resolution and the real high resolution, passing it through the discriminator to create a score.
Okay. And in this particular research, the end result looks like the underground picture,
yes,
right?
And then we were inserting the conditioning information on top of it, which is very new. So
okay.
A lot of the GAN research is done on 2D images. So we did 3D. That was one innovation. The second one was the fact that we were doing conditioning information in there too.
Conditioning on the types
on
of
the
rocks.
types of rock structures, yes.
Right.
Rock structures are in layers. They're like stratified layers.
Okay.
Like you have shale and sand and
right.
igneous rocks, different types of layers that comes in.
But if you can't see underground, how do you know which type is where?
So there is another process by which you generate the stratification from the rough stratification of the different layers. So you use that as a conditional. It's actually the whole end-to-end process is a big iterative loop. You take a stab at what the conditioning input is, then you take the low resolution image, use the conditioning to generate the high resolution, From the high resolution, you generate new conditioning input, feed it back to the image enhancer, and you generate new high resolution. In the process, you get very good conditioning input and you get very good high resolution. So it's a whole end-to-end process, is an iterative process.
I see. That's like a long process then.
Yeah, this is a long process. Yeah, exactly.
Just to make sure I understand it correctly, so you essentially guess what the types of rocks are at the beginning?
Yes.
And then you generate an image based on it and then check if that's correct?
Yes, then you go in and iteratively make it better. There's a little bit more process in there than this, but at a high level that is roughly correct, yeah.
I see. Okay.
I'd like to talk more about financial services use cases.
Okay, sure. Yeah, let's talk about it then.
Yeah, so like I said, the financial services use cases, we also have another product which is so some of the other use cases I did not cover is called redacting sensitive data. We have a API called DLP API. We also have a chatbot conversational agents, which is used very well for servicing customers. We also have a recommendation solution, real-time forecasting, and model explainability. Some of these cases in the financial services.
Right. So many things.
Yeah. Plenty of topics for ML, so we don't have a problem with finding use cases for ML. We do have to find a way to make it work in a reliable, scalable, maintainable, and portable way, and that is, I think, a big need of the hour.
Right. Okay, I'm personally kind of curious about the conversational agent part.
So the conversational agent is Google has a whole contact center AI program, but that's a much bigger initiative. But I will only talk about a subset of that, which is called Dialogflow. Dialogflow.ai is a special product we have, which allows you to build conversational agents from scratch. So it has like 3 or 4 steps. The first one, based on the user request, you built an integration as the front-end integration, which can be with a web page, it can be with a voice agent like Google Home, so it can be with messaging like Slack or Google Hangouts or any messaging service or Messenger. So in the front you have an integration. Then you have what is called an agent. The agent, each question is like an intent. So you have multiple intents, which are multiple different questions. Each intent will have multiple utterances, like several ways to ask what is your name. Okay, what do you go by? What's your name? Or 2 different ways of asking the same question. So then you train those utterances for each intent. And then the last stage is the fulfillment. The fulfillment is how to connect with the customer services, APIs, and databases in order to make it work. So basically you have front-end integration, agents and intents, and fulfillment. Those 3 stages have to be completed for Dialogflow to work fully end-to-end.
I see.
The training is for the intents.
Right. Could you maybe give us an example of how that might work?
So for example, you can do a simple web integration. So you can ask with the chat. So that's the simplest integration to do. Then you can have like 5 questions, especially in a phone call. They can ask are you making a service call? Like in a dealership, they can say, is this for a service call? Is this for buying a new car or opening a new account or whatever? So you have 5-6 questions. Each of them you train the Dialogflow agent, and then at the end it integrates with your internal processes in order to goes into your own CRM or whatever system you have in order to enter the data. The fulfillment would be like if you are going to make a service request, then it can go into your own internal service place and it will say Chanchal Chatterjee showing up at 11 a.m. with such and such car. You see what I mean?
Right.
So that's the fulfillment side.
I see. So I might call a car dealer.
Exactly.
And then the agent might say, oh, how can I help you? And
exactly. And that's a bot.
Right.
Yeah. Then you say, I need to service my car.
Oh yeah.
And then the agent will have an intent pre-programmed for that. Then it will ask what type of car, which year, make, model, what's your name, blah blah blah. Gather all that information. Then it goes to fulfillment.
Right.
In order to service that, then it'll come back and say, please show up at 11:30, blah blah place, in order to do this work.
Okay.
So that whole process is
Nice.
handled by Dialogflow.
Where is the training data come from?
Training data is for each of the intents.
Okay. Does it come from the customer or?
It typically comes from the customer, yeah.
Okay. So they might have like a bunch of recorded phone calls.
Yeah, they have, if it's text interface, then we'll have a bunch of intents.
Right.
We implemented this in several instances. We have many customers, we have used it.
I see. Yeah, I guess it's possible to solve a problem like this because the number of questions that can be asked are limited.
Yes, if it's an unlimited number of questions, like a Google Home, for example, then there could be instances where you have to learn the answer. But it's basically works best when you have a limited set of questions. Exactly.
I see. Was there anything else you wanted to talk about?
No, I think the two topics I want to stress is the AI infrastructure and the model explainability.
Okay, great.
I already talked about that.
So there's nothing like you'd like to add to this
Well,
conversation?
of course, that's not true. I mean, I can always say that building an AI infrastructure is very hard to do. So I think we should use the existing solutions that are there in order to bring your best and brightest research and projects onto that, and also take those models into production. So I think ML has a lot of innovation. I think we need to take a bigger fraction of that into production. And
Okay.
I think that's sort of a gap between what we are thinking and creating versus what we are doing.
Is that a gap between the research and
No,
production?
it's not a gap. It's
Okay.
basically the volume of research coming into play is not translating as efficiently into production solutions, especially in the financial industry.
Oh, interesting.
Yeah, in many industries like retail, because the data is locked up, it's hard to get to the data and make it work and make those models work. Even simple models taking it to production is very difficult and challenging.
Right.
So I think building these ML solutions, we need to put a lot more energy and effort into that and make it happen, is my personal opinion.
Okay. So building these ML solutions, I guess Google is one of the players that's sort of
Absolutely,
trying
the
to-
Google Cloud offers
Yeah.
such a vehicle and platform to do that. I'm not necessarily just pitching that you have to be on Google Cloud, but I'm basically saying that we need to, as a community, put more and more focus on how to be a practitioner of machine learning, how to make your models into production, how to bring more models to production, and
okay.
how to bring more models to people's use. And the rate at which we are creating new ideas and the rate at which we are bringing models is not dissimilar.
Right. So you feel like there isn't enough focus on productionizing.
I'm not saying there isn't, but we need to have more.
Okay.
Yeah.
Okay. Great. Okay. Perfect. Thank you so much
Awesome.
again.
Thank you.